Hello, everyone. Thanks for being here in person, and as well as hello to the folks out there virtually. I'm Sriram Krishnamurthy. I'm the engineering manager for Photon here at Databricks. My partner in crime, Justin, is missing today. He's on paternity leave. He had a baby a couple days ago. So excited to be here talking about Photon. The goal of this session is for you to walk away with where Photon can fit in to your workloads, whether it is jobs or as well as interactive clusters. I will highlight how Photon fits into our overall Lakehouse theme. We'll get into some of the customer scenarios where Photon has been already used and the feedback that we have received from them. And as well as we'll get into the nuts and bolts of how Photon works underneath the cover. And I will leave some time at the end of the session to take some Q&A. Before we talk about what is Photon and why it was built, let's get into the Lakehouse theme for a few minutes. So what has been happening over the course of past couple of decades is that more and more enterprises are starting to generate lots and lots of data. We're not just talking about the Googles and the Facebooks of the world, but also the small and medium-sized companies are generating a ton of data. And we're talking about scale of petabytes or more. Second, they want to start doing interesting things with the data. And we're not just talking about traditional SQL analytics, but also advanced analytics like generating machine learning models or running data science against it. Third, more and more of these workloads are moving away from on-premise onto the cloud to better leverage the available economies of scale that is available on the cloud, and as well as the commodity hardware that serves as a linchpin for the cloud is much, much cheaper than the on-premise. So this has resulted in a two-tier system architecture, where on one end of the spectrum there is data lake, and the other end of the spectrum there are these traditional data warehouses that have been resident for many decades now. So the data lakes serve as the landing spot for the data to be ingested, and they typically tend to be one of the object stores that are available. We're talking about S3 or ADLS and so forth. And they tend to be more or less in some open source format, and they're backed by, let's say, Spark as an execution engine, and machine learning models are run on top of it. Then, from the data lakes, a subset of the data lands into traditional data warehouses. We're talking about subset because it is very expensive to operate a data warehouse. So the amount of data that is really consumed from a traditional analytics standpoint is few and far between. But one good property out of these data warehouses is that they are very fast. They have their own custom encodings, and they have been fine-tuned over many, many years. And they provide fantastic capabilities in terms of access control or transactional consistency and so forth. The problem with these two-tier architecture is that, A, there are two engines that you have to deal with. They have different semantics, more or less leading to difficulty if you have to correct some data from one system onto another. Because of the fact that there are two systems, you have to create an additional ingestion step, and that means you have to maintain a complex pipeline that serves to move the data from data lakes onto traditional data warehouses. And there is no way you can maintain an access control across these two systems in a unified manner. Lastly, because of the fact that you have two systems, it's going to be expensive. And you have to maintain these systems. There's no other way out. This is where a concept like data lakehouse is very, very powerful. Databricks created this product segment altogether that has resonated so well with all the customers that other cloud providers, including Google and AWS, have created their own product segment here. And because of how well it's been received, Gartner created its own quadrant for product analytics. So the idea behind Lakehouse is to eliminate this two-tier architecture and provide a single single view of the data. And it also combines some of the nice properties of this of the traditional data warehouses into its mix. That exists in the form of strong transaction capabilities, time travel, and as well as access control. But first and foremost, it should be able to handle queries at a very, very fast pace, and at an incremental cost of what was perceived, what was consumed with the traditional data warehouses. So to create a single architecture, we need to have a single set of APIs that will work. And it needs to be backed by the fact that any kind of workloads should work against this architecture. We're talking about traditional SQL analytics, and as well as some of these machine learning and data science workloads. We also need to be able to handle streaming, batching, and whatnot. So at Databricks, our Lakehouse platform is built on Delta Lake protocol. So we are going to eliminate the data silos that was otherwise present with a two-tier architecture with a simplified and unified platform. Our Lakehouse is built on Delta Lake, which, if you have been to some of the keynote sessions yesterday, is continuously improving, both in terms of functionality and as well as performance. And it is far superior than other open source formats out there, including Hudi and Iceberg. And many of the features that we are building to improve the query performance is tied to the Delta Lake platform. Third is that we provide the infrastructure for you to run your workloads no matter what cloud you want to run it on. And your responsibility will be to build the models that are necessary to gain the data insights and do not have to worry about any of the infrastructural aspects of it. And in this talk, I will specifically get into the depths of why we have to build an execution engine that serves as a backbone for this Lakehouse architecture, and how we have built an engine that serves to cater to different kinds of workloads. Let's look into the challenges of building an execution engine for Lakehouse. Because we're dealing with Lakehouse, we're going to see data in different ends of the spectrum. On one end, we're going to have highly curated data that are going to be read by BI tools, and they are going to be in the gold tables, if you go by the medallion format that we've been advocating. And then on the other end of the spectrum, we're going to have raw files which tend to be fairly small, and they get ingested as and when they are generated, and there's no clustering or any sort of optimizations that have gone in. And in between, we're going to also have some form of optimized files. Maybe there is some amount of normalization, maybe some clustering, but they're good enough for query. The responsibility of providing a highly performant query execution falls into the hands of execution engine. So Photon is the new query engine that we built for the Lakehouse. And it is consistently faster across all the workloads that we've seen from the customers. And it provides significant cost savings because the latency is reduced dramatically. And we see up to 80% reduction in the costs. It's built for all sorts of use cases against a single set of APIs that you can use. If you've already been using DataFrames or Koalas or PySpark, you don't have to change anything. Third, with no development effort, just by enabling Photon, you can derive all the benefits. Here is a normalized performance that we have measured over the course of many years of DBR and as well as Photon. As you can see, with DBR 2.1, which was about 5 years ago, starting with 2.1, there were incremental improvements to the performance. And with DBR 8.0, we saw up to 3x performance improvement. And then last year, we introduced Photon. Right out of the gate, it was 2x faster than 8.1. and as well as 6x faster than the version 2.1, which was released 5 years ago. This is why we are so excited about Photon, and we're just barely getting started. Photon is going to help us consistently improve the performance and make leaps and bounds. Now that we have seen the reasoning behind building Photon, let's look at some of the customer use cases that we have seen over the course of the past year since Photon went public preview. Here are some of the spectrum of verticals that Photon is currently being used. It ranges from insurance, fintech, manufacturing, auto, you name it. A single consistent feedback that we have been receiving from all these customers is that the costs have dramatically reduced and the latency has reduced as well. So now you can gain faster insights to your data without having to wait for it. Let's dial into the insurance company. One of the customers who happened to be on Redshift, they migrated to Photon and they saw up to 10x improvements. Let's get into some details as far as some of the customer scenarios. So here is a media company that worked with us, and they were ingesting the raw data into the bronze tables. And they were doing some lightweight transformations of the data that happens to be in CSV format. And the sync was into a delta table. So there are two-pronged optimizations that take place. One is that the lightweight transformations are effectively written into some expressions that get executed in the Photon engine in a vectorized form. And as well as the write to the delta table is going to better leverage the parallelism that is available, and it ended up being much, much faster. So the overall outcome is that 19% reduction in the cost, and as well as 2.7x improvement in the latency. Let's get into the next customer scenario. Here is a large warehouse retailer who combined many of the aspects of the data warehouse and as well as the Delta Live table that went GA a few months ago. Here, they were using Photon in between bronze and silver conversion. And they coupled some of the other performance pack features like low shuffle merge and as well as change rate of feed. The end result was that 55% TCO reduction and as well as 5x latency improvement. The third customer that we're going to talk about is a manufacturing customer where they were aggregating the data across all their manufacturing spots across the world. And it is a very complex workflow comprising of 120 tables. And many of these tables participate in complex joins, and they face a classic dilemma of whether to optimize this job or not. And they ended up selecting Photon right off the bat. They saw 67% improvement in cost and as well as 11x latency reduction. Now that we have seen some of the customer scenarios, you probably have noticed that the TCO is significantly reduced by Photon. Let's understand why this happens. So let's say I have a job that takes about $4 totally, out of which $3 is spent on VM. Just 2x reduction in the latency will result in the VM cost henceforth being $1.5. Despite a slight markup that we have on Photon, which tends to increase from $1 to $1.45, there is still 26% TCO savings. And this is the recurring theme that we are hearing from customers, reduction in costs upon enabling Photon. Let's try to understand where Photon fits in, why it is giving a significant performance boost. So workloads may submit queries in the form of SQL or DataFrame. They get submitted to a cluster. And what we call as a cluster is nothing but a driver node followed by any number of executors that you have chosen, or you may have enabled auto-scaling as well. So it goes through query compilation, and when we say query compilation, it's all the components that a query flows through, right from parsing all the way through to the physical plan generation. And there's a lot of optimizations that happen in between. Once a physical plan is generated, this is a Spark physical plan, Photon stage compiler kicks in. And at that point, we convert all the physical plan from Spark version to a Photon version. And then we may also do some surgeries on the plan. For example, Photon does not have a sort merge join, so if the planner had picked sort merge, it will get converted into hash join, and so forth. Once the execution plan has been generated, it gets serialized, and the Spark scheduler sends that execution plan onto the executors. And an executor takes the execution plan and operates on a single partition of the data that, from the table that you've chosen, which may be in a Delta table, or it may be another table that is in non-columnar format. And Photon blends nicely with other optimizations that are being worked upon at Databricks, which is, again, like there is a metadata caching service, or there is a partition, or other performance optimizations like static partition pruning or dynamic partition pruning. So here are some of the characteristics that you would observe with Photon. First is that you will continue to see hybrid Spark and Photon plans. That is, whenever possible, we'll run a query in Photon. And when there is we run into an operator or an expression that is not supported in Photon, we will fall back to Spark. For this reason, you may see that a query will have mixed execution, and within the same task, it may go back and forth between Spark and Photon for execution. And this is completely transparent to users. This is why you can bring in your existing workloads, and they will work right off the bat without having to do any engineering. Second is that Photon has been built in the native code, and it runs closer to the metal. Why? Because if you have to build a high-performance software on Java, you are going to use off-heap memory and as well as the unsafes. So might as well write it in C++, where we can continue to control our own memory utilization and so forth. And there won't be any of the performance cliffs that otherwise would be seen with the JVM. Third, it is integrated with the Spark Memory Manager. So whatever is the agreement that's been set forth by Spark Memory Manager, Photon also follows to the agreement. So that means whenever there is a situation where there is memory pressure, we do, and Spark makes a request to us, we do spill if need be. And lastly, most importantly, this is one of the favorite properties for a Photon that helps me decide in terms of what projects that we should be prioritizing, which is because it's a vectorized execution engine, we can put lots of observability to the execution engine and decide what are the characteristics that we see from the fleet, and continue to work on features that is going to benefit our customers. So here were the key design choices that we had to make when we started building Photon. First was Spark was built with the JVM, and Photon, on the other hand, uses native code. Spark uses code generation, and Photon uses vectorized execution. And lastly, Spark works on a row-by-row basis, whereas Photon works on a column basis, batch of row basis. Before we get into vectorization, let's look at what Spark currently does underneath the cover. Let's say you have a simple query that scans a table, scans one of the columns from a table, it runs a filter, and then it does a simple expression, which adds a column to a literal that was passed in. Here you can see the code that was generated by Spark. It's a Java code, and they get run in a tight loop, because of which they're going to be fast. But The problem with this model is that it is very, very complex to generate code that generates code, and even more difficult to debug. Let's look at the same code that we use for vectorized execution. In this case, the vectorized execution preserves the operator boundaries. It kind of looks like how an interpreted execution would look like, except instead of operating on a per row basis, it is going to operate on a batch of rows or batch of columns basis. So in effect, this gives the simplicity of the volcano model with the performance of the code generation model. Here's an example of one of the operators that's been implemented in Photon. So we have a hashing aggregate, and there are a couple of steps where we could leverage the vectorization. First is that to generate the hashes for the hash table from the keys, in order to look up this hash table, which may be outsized and outside of the core, first we use SIMD to compute the hash of the keys. Second is that to probe to do the actual probing, we can leverage the parallelism within the CPU and the memory to issue multiple loads to the hash table all at once. This, in essence, speeds up the aggregation processing tremendously. If you look at some of the benefits of the parallelism, you can see that the independent loads result in the TLB misses dramatically. And more time is spent by the CPU doing the actual work than waiting for the cache to be loaded. Thus, there are three distinct advantages of vectorization against the code generation. First is the human factor. Whatever we use underneath the cover is nothing but a vanilla C++ code. Maybe there is some templating to avoid otherwise what would have been a redundant implementation of the code. It is much easier to optimize and debug vectorized code than the code generation model. The second is that there is a strict maintenance of the boundaries between the operators. This allows for us to inject metrics collection, and we can decide on what sort of effort we need to put in order to make improvements to the fleet. On the other hand, if you have code generation, generating metrics is very difficult, and you are more prone to introducing performance regressions because they're all squished together. Third is that vectorization gives us the benefit in terms of adapting to the workloads that are seen in the lakehouse. This is one of the key reasons why we built an execution engine right off the scratch. For example, we may see that the data that let's say we are doing a string processing, and the data that we are consuming happens to be UTF-8. In certain scenarios, it may be that there is for the batch of rows or batch of columns that are currently under process, they are all single bytes, in which case we can take an optimized path than otherwise if it happens to be multi-byte. And these sort of speed ups provide significant overall latency reduction. So now that we got into the internals of Photon, so why should we integrate with Spark? Why not just run everything in Photon and fail the queries otherwise? And maybe we could use existing Spark scheduler and the coordinator. One, we wanted the existing workloads to be run on Photon without without our customers having to put any engineering effort. There are thousands and thousands of workloads that have already been written, and it would be enormous effort to re-engineer those workloads to run only on Photon. Second, and more importantly, as we continue to improve Photon and add the capabilities that are missing, we can roll them out incrementally, and whatever was earlier running in Spark would just get changed to run on Photon, and without having to, without any investment from the customers. So this is one of the reasons why when you enable Photon in your workload, you may continue to see some parts of queries being run in Photon and some being run in Spark. So now that we know that Photon is going to have a hybrid execution model with Spark, let's see how this happens underneath the cover. Let's say I have a query that scans a table, runs a filter, and does an aggregation, and finally does UDF evaluation on Python. So if the scan and the Python execution were to not be supported by Photon, and that is the case currently, here is what will happen. When the scan will, let's say we are scanning data source V2, which is a popular model for extending the scan capabilities in Spark, and they all generate row-wise data. So there is going to be an adapter that is going to get placed between Spark and Photon, which converts the row major format into a column major format. The filter and aggregation will get operated on a batch of rows, and then at the transition point, there is going to be another adapter that will get placed, which will convert from columnar representation into row-wise representation. And the unsupported Python UDF expression will get executed in Spark and will be given back to the client as far as the result is concerned. So one very cool achievement that has come out of Photon is that, at least in part because of the Photon and the host of other improvement that's been going on at Databricks, is the first ever submission that was placed to the TPCDS Council in terms of the 100 terabyte measurement resulted in 10% reduction in TCO. For folks who are not who are not aware of TPCDS, it is the gold standard as far as the benchmark is concerned. And it does a whole host of things. It loads the data, it measures the raw query processing time, and as well as the concurrency aspects of the system. And 10% reduction over the next closest system is not something that is typically seen, and that too for a cloud-native system. So where are we with regard to Photon? Where are we heading? We began the effort to build a new query engine almost 4 years ago, and the result of it was the public preview release in June 2021. And since then, there's been a host of features that have been released, including addition of instance types, array and struct support, additional aggregation functions, and as well as we've done a preview on some of the key operators. If we go back and into few slides earlier, and one of the key capabilities out of Photon was the ability to measure metrics. And we saw a lot of customers were running sort and window functions in their workload. We began the effort to support those features natively in Photon. The result of it was that we had a private preview up and running for the past 3 months, and we've been getting excellent feedback on it. So at this juncture, Photon is battle tested. It has answered billions of queries, processed exabytes of data, and handled mission-critical analytics for a host of customers. With that, I'm super excited to announce the general availability of Photon in the coming weeks for the workspaces. With the general availability, we're also going to support vectorized sort. And this is a sort that is going to be highly adaptive. It's going to look at what sort of workloads what sort of data characteristics your workload has, and appropriately choose a sorting algorithm underneath the cover. Second, we are also introducing accelerated window functions. This includes support for shrinking, growing, unbounded, as well as running frames. And there are 9 new window functions that are going to be supported, all implemented using the vectorization model. And they're going to provide you with significant speed ups if your workload happen to have sort and window in them. Lastly, we are expanding the capability as far as the scan sources is concerned in Photon. Earlier, there was only Parquet and Delta support as far as the scan sources is concerned. Now, we want to extend the capability of Photon to go after raw data sources, which could be in the form of CSV, JSON, DataFrame caching, which if you had participated in the preview and lack of which was causing the workload to not run in Photon, henceforth will run in Photon. So here is here are the list of data types, operators, and expressions that we support. As you can see, the bread and butter of what is expected from workload perspective is there in Photon. There are a couple of caveats, of course. One is that if you have RDD scans, if you're using RDDs heavily, recommend converting them to data frames, because RDDs are essentially Java objects. There is going to be significant cost for us to convert these Java objects into the Photon native representation, and we may not be able to amortize the costs. Likewise, the same argument also holds true for the Scala UDFs. So if you happen to have Scala UDF, we will support Python UDFs in the near future, and they will get Photonized. So what's coming next? We're going to continue to work on improving the latency aspects, particularly around the BI workloads. Additionally, we will also improve the capability in terms of concurrency aspects of these BI workloads. We'll continue to factor in more improvements to the window functions, and we'll also add top capability, which is again a very common use case for the BI workloads. We will support Python and Panda UDFs in near future. And we're going to extend the applicability of Photon as far as the raw data source processing is concerned. We will we will release support for additional aggregation functions in the form of for you to do the deduplication. And we are also building a native JSON scan capability, which we are super excited about. And it provides almost 5x improvements compared to the parsing capability in vanilla Spark. And lastly, as an execution engine that's been built to accelerate your performance, we are going to continue to invest in terms of providing better price to performance. And that includes in the form of building native scans for Parquet and Delta, and building and extending the scan capabilities to also include other optimization techniques like lazy materialization or dictionary filtering. And as well as we see there is a potential for improving how shuffle works underneath the cover, and Photon is going to make this better. So now that you've heard about Photon, how can you go enable Photon? So it's very simple. If you happen to have Terraform scripts that you use to create these clusters, you just set Photon worker enable to true, or otherwise you can go to cluster manager and you check the use Photon acceleration box. So here are the key takeaways. We built an execution engine that is going to help us to continue to make improvements in terms of our Lakehouse story. And we're just barely getting started. We will continue to make these improvements such that your workloads will become cheaper and cheaper over the course of time. In its current state, you will see that the workloads result in up to 80% reduction in your costs, and as well as 12x better price to performance. Photon is an engine that's been built for all sorts of workloads. You don't have to think about the applicability of it. You can use it for BI, you can use it for streaming, you can use it for ingesting the data from different sources. You can run complex ETL on it. Photon will be able to give you the price reduction that you're expecting. And lastly, most importantly, you don't have to make code changes, barring the RDD and the Scala UDFs. So here is the call to action. If you're convinced of Photon, please go and enable the checkbox today in your cluster manager and give us the feedback about, and we look forward to hearing from you. Thank you. Do we have time for questions? Yeah.
In the hybrid execution model, the Photon actually takes an operator which is not supported, and let's say it's running on 2-3 billion rows. Now it's going to have to push all these 2-3 billion rows into the JVM. Is this not an overhead? Is this not really creating a burden? Heavy,
To restate the question, what will happen if there is an operator that is not supported in Photon happens to be encountered, right? So there is going to be costs. It also, at this juncture, we have seen most of the operators that are computationally expensive, they are supported in Photon. There may be outliers that you encounter, which will cost the operator, which will cost the execution to exit Photon and run in Spark. But there are other considerations that we are thinking of where we can come back to Photon, as long as there is enough of downstream operators that are expensive and they can run faster and we can amortize the cost, we will come back to Photon.
I see. Another question I have is on Scala UDF. Before Photon, we were supposed to use the Scala UDF and avoid Python UDF. Now it's, I guess, reverse, right? Now we are encouraged to use Python UDF.
Yep.
And not the Scala UDF.
So we're not closing the doors on Scala UDF, just to be sure. We at this juncture, the cost for converting from Scala representation or effectively Java object model representation to Photon is high. And we are still investigating whether that can be reduced, right? So if we are able to reduce it, then we'll support Scala UDFs. But just the nature of the fact that we have an engine that is written in the native code, and you have to convert from object model in the Java to the native internal representation of Photon, it's expensive. And there is no point in, like I said, doing that conversion unless you can recoup the costs. So maybe we will factor in.
No, the problem is if you're running in this hybrid mode, then you don't know, because if you're running in hybrid mode, of course you incur a big overhead if you have Python UDF. Now, unless everything is photonized, that your Python UDF is not going to run in a Python interpreter.
Yes,
so basically, this is a kind of a catch-22, I see, because.
No, for Python, we can make it faster because we can do out-of-order evaluation of the Python UDFs. And because of the parallelism that is there, we can run them faster. Right? For the Scala, just because of the conversion cost, and there's also the serialization with regard to serializing the data from Photon to Python, we can pass it in an optimal format where it's not going to be too expensive to convert. On the other hand, the Java object model is such that it does not play well with the Photon internal representation.
Got it. So
that is why we are advocating. We understand that there are going to be certain customers, their developers tend to be comfortable with Scala UDFs, and they will have to continue to use it. Right? But by and large, if you look at PySpark, the amount of downloads that's been happening and how the ecosystem has taken off, we see the trending in that direction, which is why,
correct,
and also plays nice in terms of our future plans.
Got it. Thank you.
Are you planning to look at even more lower latency workloads, more like OLTP, TPC, C benchmark kind of things, or is it not in the roadmap yet?
Yeah, I didn't share it in the roadmap, but yeah, there is a strong focus in terms of handling low latency workloads, including thousands and thousands of queries, especially on Monday morning when all the analysts dial in and they all need to generate their report. That means they all want the low latency reports running concurrently at a fraction of the cost that otherwise would be taking place. So yeah, there is effort going on in that space.
Is there an additional cost?
Sorry?
Is there an additional?
Yes. So Photon, there is a multiplier, and I believe there is a pricing change. So right now, in fact, the pricing change is going to go in on July 1st. So yeah, so there is a multiplier that's placed on Photon because of the acceleration. But you got to look at the overall TCO, right? So when you look at the cost savings that you're getting, and the VM cost is going to get dramatically lower, and even with the marginal multiplier that we place on it, you will still see significant reduction to the TCO.
As a follow-up, in your opinion, or in your observation, have you come across what other components companies dismantle because of the improvement?
What other? I mean, we haven't seen like getting dismantled, right? So maybe that is a question for product who's not here, but Photon is a big differentiator for us at Databricks. We see a lot of customers migrating their workloads from other cloud offerings onto Databricks just because Photon, right? And there are so many reasons why the dismantling is not going to happen right away, right? So.
You mentioned that you're adding observability.
Mm-hmm.
There's going to be open source integrations, or what? How are customers going to be able to?
So it's two-pronged. One is that the observability metrics are on one end of the consumption is for us internally to improve the product. And the second is that the aggregated metrics will be displayed to customers in the Spark UI. And you can see what has truly happened. When Spark displays some of the metrics, it can be a heuristic at times just because of the code generation that I explained. We got to be very careful about where we place these observability metrics. Otherwise, it'll cause severe performance regressions. Good.
I used it in preview, but on July 1st, it's going to be open to many different types of nodes, or is it going to be to such a limited set of nodes?
So as far as the instance types, there are no new instance types that are getting released on July 1st. It's just the pricing. We were in a promotional phase for a while, and we're going back to the original price. But despite the pricing being brought back to its original price, the TCO is still going to get reduced for your workloads.
Right. I guess the motivation for the question is that at least on Azure, the instance type.
Oh, sorry. Okay,
It's specifically scarce in some regions.
Yes. Okay, I'm glad you brought it up. On Azure, I thought we already released, but maybe it's not documented yet. But we are adding a host of instance types on Azure.
Oh, wonderful.
Yes.
Just want to follow up on the pricing question. So is Photon actually going to be a price on the SKU list, or is it just going to be a process that that basically that the query will just be optimized to run either on Photon or Spark, depending on what the query includes?
No, at this juncture, it's already a SKU. So when you check the acceleration box, it's going to get built under a different SKU altogether. Yeah. right, thank you, everyone.